Everybody. So welcome to part two of our lecture series on light. So just to do a quick recap, in part one, we talked about the basic physical properties of light and um, just answering the question of what is light. And in that first part, we discovered that, hey, light actually behaves simultaneously as a wave and as a particle. So in this part two lecture, we're going to be diving deeper into the wave properties of light. So it's going to be very helpful to learn some sort of terminology that's going to be associated when you're studying any type of wave, whether that's going to be a light wave or a sound wave. So this type of terminology that we're going to be learning is going to be just helpful in analyzing all kinds of waves, mainly in this case, of course, light waves. Okay. So a property that any kind of traveling waves have is something that we call a wavelength. So sometimes if you read this or look this up in different resources, it's usually going to be denoted as the Greek letter lambda. And by definition, the wavelength is the peak to peak or the valley to valley distance. So here I'm showing you guys a bunch of very predictable waves. So they just go up and down, up and down. And so, for example, I can label for this red wave here the wavelength just from using the definition. Okay, so if I take my peak here and measure how far that is to the next adjacent peak, like you could literally, in principle, take some sort of measuring device of distance and get some number out of that, that will get you the wavelength. And again, so this is peak to peak or valley to valley, so that means I could have also equivalently measured, this valley and how far that is to that valley next to it, and you will get the same number if you measure the peak to peak or the valley to valley distance. Same thing, okay? And then also, if I take another wave here, let's take the wave here in the bottom, the purple one or the violet one in this case, and I measure the same idea here. Let's this time measure the valley to valley distance just to kind of change it up. And now I'm showing you another wavelength. And you can see here that the wavelength of the red wave is going to be shorter than the wavelength of the violet wave. So here's the key idea when you're talking about light waves. When I talk about different wavelengths of light, that actually corresponds to different colors of light. So those are synonyms, essentially. Different wavelengths means just different colors of light. And in this figure, it kind of nicely illustrates how the wavelength of light changes and how they're associated with colors, because you can see here that the longer wavelengths correspond to the redder shades of light, and then you have the shorter wavelengths correspond to the bluer shades of light. Okay, so that's just kind of a way to simply understand how the wavelength of light changes, at least for the colors that our eyes are able to see. Okay, and because light travels, then we should also talk about the speed of the wave. So that tells you essentially just how fast the wave is traveling or how fast it's propagating through space. And so here's a key idea. All waves of light travel at the same speed, and that is at the speed of light. Okay, that is a key idea that you're going to have to remember. So for example, if this wave that I'm showing you guys right now is a wave of light, you can see that it's moving to the right. And so therefore that wave, even though it doesn't look like it, but if we're going to classify it as a light wave, that light wave has to move at the speed of light. Okay. So the next property of wave that you're going to have to be familiar with is something that we call the frequency. So the frequency is defined as how many cycles passes by in some specific point in space in a given time. And usually that's going to be measured in hertz. Okay, so let me just show you this animation here to kind of illustrate what I'm talking about. It's best seen through this animation. So let's say I am just picking some sort of region in space, okay? And you can see here that if I just hover my mouse here, and you can literally count how many cycles of the wave passes through within some given amount of time, you can see that this wave on the top is happening, or the cycles are happening more frequently than the wave on the bottom. So you can kind of conclude that, hey, these two waves are different frequencies, and the wave on top is at a higher frequency than the wave on the bottom. Another thing to note here too is that the waves are both traveling to the left, and you can see how fast they're traveling relative to each other. And so these two waves, this is a good comparison because these two waves are actually traveling at the same speed towards the left. However, they have two different frequencies, the top one being of a higher frequency. So something that you might compare this to is, for example, whenever you buy a brand new TV, something else about the TV is measured in hertz, and that's usually the refresh rate. Another word for that is called the frames per second. So for example, if you have a TV that is of 30 hertz or 30 frames per second, that means that the TV cycles through 30 times per second. So that means it's changing its screen 30 times per second. And that's usually kind of the threshold that your eye is able to tell the difference, whether something is like going to be smoothly animated or going to be like choppily animated, okay? So, you know, anything higher than 30, your eye actually can't visually tell unless you put it into slow motion. Okay, so in this case, we're talking about waves that are kind of getting refreshed. And so you can see here that the top wave kind of cycles through 8 times through some given amount of time. Every time the bottom wave cycles through 2 times. So there's like an 8:2 ratio here. Okay, so now let's put it all together, combine all of those ideas. So all light waves travel at the speed of light. And so you can kind of notice now, if all of the waves are traveling at the same speed, then that means that if you have a light that is of longer wavelength, that is also synonymous with saying that the light has a smaller frequency. And if you have a light that is of shorter wavelength, okay, then that means that corresponds to light having a larger frequency. So here's kind of an animation that I put together to illustrate these two ideas. So when you saw that animation, both of the waves are traveling at the same speed. However, one of them is at a higher frequency and the other one's a smaller frequency. So let's just play that one more time. Okay, and then one more time again. Okay. So it's happening a little fast, so feel free to just kind of pause that if you want. But yeah, that's essentially the point that I'm trying to make here, right? That whenever you're saying one property of light, that actually also means another property of light, okay? All right, so we've kind of just been talking about it briefly, but now let's kind of formalize this terminology here. So our eyes are only able to see specific wavelengths of light, okay? So we are just biologically engineered to see specific colors of light. We can't really do anything about it unless we evolve somehow to be able to see other wavelengths. And so that range of wavelengths is called the visible light spectrum. And remember, different wavelengths correspond to different colors of light. So you can see here the range, the full range that we're able to see. You can see that it's about 400 to about 750 nanometers. So nanometers is very, very small. That corresponds to 10 to the negative 9 meters. If you had to compare that to something maybe that you're familiar with, that's comparable to the size of the bacteria in your gut. Okay, it's about that size in terms of the wavelength. And so red light, as we saw in the previous figures, that's actually the longest wavelength of visible light. So that has about 750 nanometers of its wavelength. And then blue light corresponds to like some of the shortest wavelengths of light that we can see, corresponds to about like 400 nanometers in wavelength. Okay, so you might be asking, okay, why do people typically refer to it as like blue light and red light versus like red light and violet light, which is really the shortest one, right? I think it's probably because, violet light has like 3 syllables and blue light has like 1 syllable. So we just say reddish or bluish or red or blue. So it's much easier to just compare, okay? And you can also see here that, all of these colors that we're able to see in the visible light spectrum correspond to the colors of the rainbow, right? Roy G. Biv in that specific order. So when you're actually saying Roy G. Biv, you're kind of sorting the wavelengths of light in ascending order. Like longest is red, and then shortest is violet light. Okay? All right, so what about the whole light spectrum? The whole light spectrum is called the electromagnetic spectrum. So remember, light is an electromagnetic wave. So therefore, you have to include other wavelengths outside of the visible light range. And so here's kind of a figure to illustrate that. So if you look at my mouse here on the figure, I'm kind of hovering over it. And this is sorted shortest wavelength on the left and then longest wavelengths on the right. And in terms of frequency, that also tells you highest frequency on the left and then lowest frequency on the right, because those two things are synonymous. So this is kind of sad, right? Because if you think about it, if this is the whole spectrum of light, we are only able to see this much of it, right? This little sliver of it corresponds to the visible light spectrum. However, when it comes to longer wavelengths, we can't see infrared, microwave, and radio waves. And when it comes to shorter wavelengths, we can see UV, X-ray, and gamma rays. So we actually have a lot of applications for different types of wavelengths. So for example, the wavelengths that we're not able to see on the longer end, infrared basically means light that's going to be produced through some sort of thermal process like heat. That's why sometimes when you wear thermal goggles, if you point it at people or any kind of living organism that emits a lot of heat, they glow very, very bright. Okay, so infrared corresponds to kind of emission of light from heat. And then microwaves and radio waves, they are mostly used for communication purposes. Well, microwave specifically actually is going to be the same waves of light that your microwave oven emits through your food, because your food contains a lot of water, and water is a good absorber of microwave light. It causes the particles to vibrate, causing it to heat up. And then for radio waves can basically go through anything, and so, or at least it can kind of bend around different barriers. And so we use that a lot for communication. So for example, whenever you're making a phone call with your cell phone, or kind of using your cell phone for internet, then that means that you are receiving and also emitting radio waves from your phone. And then for UV, you typically used for forensic purposes, to kill germs, and of course, when you get UV light on your skin, you want to block that, because that's harmful for your skin. That can cause skin cancer. And that kind of also illustrates an important property of light. It carries energy. And so when it comes to energy, the shorter wavelengths actually carry a lot more energy than the longer wavelength light, right? So that's why, for example, when you go to X-ray, when you go get yourself an X-ray, and at the dentist, they make you wear some sort of like shield, an X-ray shield, to protect your body from that X-ray light. And then gamma rays. Gamma rays, that's going to be in terms of like just not necessarily useful, but more like where we use it. Gamma rays are going to be produced when you have nuclear weaponry. When you have nuclear weapons, gamma rays are usually produced because they carry a lot of energy, very destructive energy, right? And so now you can kind of see here, right? Now you have another kind of um, I guess, physical quantity to work with, which is energy. Shorter wavelength means higher energy, and then uh, longer wavelength means lower energy. So what I typically like to do is come up with some sort of like mnemonic or some sort of like gesture to remember all of these variables, all of these physical quantities about light. So for example, if you take your finger, you go like this, right? And you kind of like do a very slow wave with it, right? And so that corresponds to like longer wavelength, right? Smaller frequency, and it doesn't take that much energy to do. And then if you do this, right? Very frequent, very high energy, short wavelength. So now you'll never really forget which is which, okay? All right. So speaking of energy, so let's just kind of formally define uh, what energy is. So the energy is the capacity to do work or usable power. And energy usually comes in different forms. And so you've probably heard the phrase where energy cannot be created or destroyed. You're just kind of converting one form of energy into another form of energy, right? And that's actually a true statement. So for example, you have wind energy here. So wind energy, you can classify that as some sort of like mechanical energy, something that's moving, has some sort of energy, and you can convert that into some sort of electrical energy. You can use that to power your house. A lightning, for example, carries like electric energy. Okay, if you can harness the power of lightning, then you can use that into some sort of usable energy. Whenever you're eating food, for example, food has a lot of stored energy. So you are converting that by digesting food. And now you can convert that chemical energy that the food contained into some sort of usable mechanical energy. Okay? Now, light carries energy, and the energy that we use or that we call the energy carried by light is called radiant energy. Okay, and so when you're talking about light, kind of just reviewing, light carries energy no matter what kind of wavelength you're using, and again, longer wavelengths carry less energy, and then shorter wavelengths carry more energy. So this kind of opens up some sort of discussion, right? Because now when you think about it, radiation basically just means light. And usually when you say the word radiation, that kind of invokes some sort of negative emotion towards it because people get scared. It's radiation. It's harmful to our skin. It's harmful to people or to life forms. But really, maybe a follow-up question to think about is like, okay, well, what kind of radiation are you actually receiving? Because we're receiving radiation right now, all right? Like I am receiving light coming from my room, and that's radiation, but I'm not freaking out because that's low energy radiation, right? For example, whenever you have sunblock, you never buy sunblock for microwave or infrared or radio waves. You buy it for UV because that's actually a type of radiation that's harmful to you. Okay, so when you're thinking about radiation, make sure you apply some sort of critical thinking. Okay, well, is all radiation harmful in the first place, right? What kind of radiation are you actually receiving? So something to think about, keep that in mind. Okay, so let's bring this back in the context of astronomy. So the sun is going to be our major source of light, and along with other objects as well that can emit a lot of light. And so, what kind of light does the sun emit? Well, it actually emits light from all different types of wavelengths. However, it emits more light in a specific wavelength more than the rest. And so the Earth has an atmosphere, and the atmosphere acts like some sort of like screen that covers or blankets the whole Earth. And so this picture is actually showing you what types of light the atmosphere of the Earth allows through it, and how far different types of light penetrates below the Earth's atmosphere. Okay, so over here, this is basically like the upper regions of the Earth's atmosphere in this figure that I'm kind of circling around. And then over here is the very surface of the Earth. So basically, you're like standing on the surface of the Earth when you're at sea level. Okay, so you can see here, right? And thank goodness that the Earth has this type of property that has an atmosphere that you can see it blocks out a lot of the shorter wavelength, high energy type of light. Otherwise, if they were all to reach Earth, then we would have some major issues with the life forms that are living on Earth, including us. Okay? Visible light, you can see that it penetrates all the way down towards sea level. And again, thank goodness for that, because our eyes are accustomed to seeing visible light. Otherwise, everything on Earth would be dark if our atmosphere did not allow visible light to penetrate through. You can see that for infrared, the Earth's atmosphere is like partially transparent. You have to go like high enough above the Earth's sea level to actually be able to detect infrared light. And then for radio light, this is why we use radio for communications, is because radio is able to move around the Earth or around the surface of the Earth, and it penetrates all the way down as well, from the upper regions to the lower regions of the Earth's atmosphere. So really, when you look at this, there's really only two windows of light where the Earth's atmosphere is fully transparent to, and that's going to be the visible light and radio light. Okay? So when you consider all of the different telescopes that the Earth, or that we have on Earth, you can see now that this is basically a figure that shows you where all of these telescopes are situated. Either they're going to be in space, or they're going to be on the Earth's surface, or somewhere in between. In the case of Sophia here, which is basically an infrared telescope that's installed on an airplane that's just kind of moving around. So you can see why, for example, that all of these telescopes that are observing in the shorter wavelengths are going to be placed above the Earth's atmosphere, because the Earth's atmosphere blocks a lot of that type of light. So in order for you to quote unquote see in the gamma rays, the X-rays, and the UV, you have to have telescopes above the Earth's atmosphere, or in space, essentially. However, when you're looking at the longer wavelength range, you have the option of saying, hey, we can actually build a telescope on the ground, because again, you have visible light penetrating all the way through. Or if you want to just remove the effects of the atmosphere, because another effect of the atmosphere is that it blurs out your images, you can build it above, and you can build it in space, or launch it in space and have it take data while it's up there. Okay? And so you've probably heard the quote where, I'm paraphrasing here, where if you look at anything in a different kind of light, you'll learn new things about it, right? So that is super true for astronomy, right? That's why we have all of these different telescopes looking at different colors or wavelengths of light, because every single wavelength kind of tells you something different about whatever object you're looking at. So I'll give you an example here. So this is the Andromeda galaxy observed at different wavelengths of light. So you can see that it looks vastly different. For example, visible light, and comparing that to the radio and the X-ray images. So the radio and the infrared, for example, is telling you where all the heat or the thermal emission is, where the dust is contained in the galaxy, and mostly it's in the outer regions along the disk of the galaxy. And so that's important for astronomers because that tells you where all the brand new stars are going to be forming. Okay, so they're sites of star formation. The visible light, the fact that you're seeing so many different colors there, tells you that you have a bunch of different colored stars that are living in the galaxy. And here's a pattern that you can see. On the outer disk of the Andromeda galaxy, it's bluer, and then on the inner part of the Andromeda galaxy, meaning the central part, is redder. And that also tells you something about the relative ages of the stars that are living in that galaxy. So the outer disk contains usually younger stars or bluer stars, and then the central part contains older stars, which also makes them redder stars. We'll talk more about that later, but essentially that's the big idea. The ultraviolet tells you where the hottest, bluest stars will live because they emit a significant amount of UV light. But also, in addition to that, that also tells you where some of the hottest gas is in the galaxy. And usually that's going to be in the very central part. And in addition to that, if you look at the X-ray, X-ray does the same thing. It actually tells you where the hottest gas is inside of a galaxy. And you can see here that it's actually concentrated at the very, very center. So now you might ask, what is the source of X-ray light in a galaxy? Like, why is it all there? So that's essentially the supermassive black hole that lives at the very center of the Andromeda galaxy. But wait, it's a black hole. How is it emitting any kind of light? I thought black holes actually absorb all light and it doesn't let any light back out. Well, it's actually not the black hole per se that's emitting the light. It's the stuff swirling around the black hole. And so the black hole is this very massively dense object. And what it's doing is that anything that's going to be in its immediate vicinity, it's going to be orbiting pretty fast in order to not get sucked into the black hole. And so if whatever is orbiting really fast is some sort of gas, then that gets heated up at a very high temperature. So it gets really hot to the point where it's actually going to start emitting a lot of X-ray light. And that X-ray light is what you're seeing at the very center of that galaxy. Okay? So another picture here is basically our sun. So you have two comparisons here. You have the visible light and the X-ray light coming from our sun. So visible light, so our sun actually is the biggest emitter of visible light in our solar system. And the visible light, it's kind of boring, right? If you look at it, it's you can see a couple of sunspots here, a couple of those cold spots. But other than that, you don't really see much features. It's not actually until you start analyzing the different wavelengths in the visible light that the sun is emitting where it gets a little interesting. We'll get to that later. However, if you look at the X-ray light, that's where it's really interesting because now you're seeing basically the hottest regions of the sun here, and you can see a lot of loops that are happening on the surface of the sun. And all of those loops are happening because you can actually model the sun as some sort of gigantic magnet. And magnets form a lot of like magnetic field loops. And the loops that you're seeing here are basically the gas that's kind of tracing those magnetic loops. So we'll talk more about that later when we start jumping into the sun by itself. But for now, you can kind of see, right, how the visible light is vastly different from the X-ray light. Okay, so last thing, if you look at another object known as the Crab Nebula. So first off, what is the Crab Nebula? So the Crab Nebula was formed because of a massive explosion that happened called a supernova A supernova happens basically when a star is very close to its death, and then the explosion kind of just finishes the whole process. And so, whenever a supernova happens, something is usually left behind, either some sort of like remnant called a black hole. So that's one. You guys already know what a black hole is, or a neutron star. So in the case of a Crab Nebula, there's actually going to be a very, very tiny star called a neutron star right at the very middle. And so the first observations of the Crab Nebula were happening in the visible, and I think this is probably why they call it a Crab Nebula, because maybe the top part of the crab, like the crab, the animal, kind of looks like the Crab Nebula. That's what I'm guessing. Um, and so you can see that it's very, very complicated looking in terms of the visible light. And that kind of just tells you all the heavier elements that are producing that light that are all present in the supernova process. So by analyzing this light, you can tell, right, the composition of that of the star that actually exploded. And then when you look at UV and the X-ray, so that carries a lot of energy, and so that tells you where all the hot gas is, or the hottest regions within that nebula. And so that tells you, again, like the regions that are closest to the neutron star at the very, very center of this nebula. So it probes those specific regions of high energy, hotter gas. And then when you look at the infrared emission, that tells you where all the heavier elements are that contains dust, and also some sort of like thermal emission, in other words, heat. And then radio tells you where all the molecular hydrogen gas is, so H2 gas. So that's important because supernova, when they inject all of this cold molecular hydrogen gas everywhere in space, that is the key ingredient to form brand new stars. And so it's kind of interesting, and we're going to go back to this later. It's a cycle. The death of a star from a supernova can potentially trigger the birth of a new star. Okay? All right, so that's about it for this segment. Next time, we're going to be talking about how light interacts with matter. See you next time.